Hello there all. So this is the third video of section 1.3 where we're going to be talking about vectors form. So we're going to introduce some new notation, one new definition, some interesting geometric examples, and then we're going to go through a couple concrete examples in this video. So let's suppose I've got the following vector equation. X1 times A1 plus X2 times A2 plus XP times AP equals B. So I'm writing this equation now a little differently than we've seen vector equations written in the first two videos. Namely, here X1, X2, and XP are going to be variables in this equation. And so sometimes we write out this equation with the purpose of asking, can I find X1, X2, up through XP that make this equation true for a given set of vectors, A1 through AP and B. And so if you remember from the last video, this amounts to asking the question and solving the question of whether or not B can be written as a linear combination of A1 through AP. And as we had seen, this equation has the same solution as the system whose augmented matrix is given by this matrix. And now this notation is new. And what this is defining a matrix by its columns. And so what this is saying, okay, this augmented matrix has columns equal to vector A1, vector A2, vector AP, vector B. As an example, if A1 was equal to the vector 1, 2, A2 was equal to the vector 3, 4, and B was equal to the vector 5, 6, then the matrix A1, A2, B would be equal to 1, 2, 3, 4, 5, 6. So it's just a way of writing out a matrix by specifying its columns. And so it's just sort of a shorter way of writing a matrix, especially if we already know what these vectors are. It's a way of quickly defining this matrix. And if you remember from the example we saw last video, this is exactly how we solved this vector equation, or in other words, determined if B was a linear combination of A1 through AP, was we set up the augmented matrix corresponding to a system of equations that was defined by sort of this vector equation. Remember, we could sort of break it down the vectors, where here vector A1 represented all of the coefficients with X1, A2 represented all of the coefficients with X2, and so on. So we have a special name for the set containing all linear combinations of a set of vectors. And you will hear this term thrown around quite frequently throughout the rest of the course. So if I have a set of P vectors V1 through Vp, so if V1 through Vp are a set of P vectors, then the set of all linear combinations of these vectors is called the span of V1 through Vp. And we'll often denote it with span set V1 through Vp. So what this is a set containing every single vector of the form C1 V1 plus C2 V2 all the way up through CP VP. So if I have a vector b that can be written in this way, then we say that V is in this span of vectors. So anything that is a linear combination of V1 through Vp is said to be in the span of V1 through Vp. And so this is just a nice sort of compact way of describing the set of vectors that can be written as a linear combination of vectors. And so now asking the question, is B a linear combination of V1 through Vp, is just equivalent to asking, is B in the span of V1 through Vp? And so with this definition, I want to give one example of sort of what a problem might look like. You might be starting to notice early on here in linear algebra a trend of sort of using the same method of row reduction to often solve a lot of problems. And so oftentimes, and I feel like the beginning of this course is especially true, that this course is sort of, could sometimes be called, how many ways can we word the exact same problem? Because that's often what's going to go on here, is that the solution to most of these problems we present is just going to involve setting up a matrix and row reducing. And so we want to know if we have these three vectors, A1, A2, and A3, is B in the span of A1, A2? And so I'll make A2 a little more clear here. A1 is the vector 1, negative 2, 3. B is the vector negative 3, 8, 1. And A2 is the vector 5, 13, negative 3. So what this question is asking, again, does B equal C1 A1 plus C2 A2 for suitably picked scalars C1 and C2? And so if you'll remember, solving this question is equivalent to solving the linear system of equations, which I'll write down. So it is equivalent to solve the system x1 plus 5x2 is equal to negative 3. Negative 2x1 plus 13x2 is equal to 8. And 3x1 minus 3x2 is equal to 1. And so remember, how do we solve this? Well, we set up an augmented matrix, of course. And now, once we have our augmented matrix, we just put that matrix in reduced row echelon form. All right, so first things first, I'm going to do a couple row operations right off the bat. We'll do negative 2 row 1 plus row 2 to replace row 2, and negative 3 row 1 plus row 3 to replace row 3. And so notice what this is doing. I'm doing both these operations at once, sort of just to save time and space. I've chosen 1 to be this pivot entry, and so I'm going to use the 1 to get rid of this negative 2 and this negative 3. And so doing both of these row operations, I should get the following matrix. Well, row 1 should be left alone. And I get 0, negative 3, negative 2, and 0. Sorry, I wrote this wrong. A2 should actually be negative 13 here. So when I was copying this problem down, I wrote positive 13. A2 should be negative 13, and so this would correspond to minus 13x2. I apologize for that. just change this to negative 13 minus 13. In this matrix, this would be a negative 13, and then you would actually get a negative 3 there. So I apologize for that. Continuing on with this, I get negative 18 there. And last but not least, I should get a 10 here. All right, so now again, if I'm row reducing, I want to make this negative 3 my next pivot entry. So what I'm going to do is I'm going to use the negative 3 to get rid of that negative 18. So I'm going to do negative 6, row 2, plus row 3, and I'm going to replace row 3. And this gets me 1, 5, negative 3, 0, negative 3, negative 2, 0, 0, negative 2. And at this point, I claim we have enough to answer this original question. So remember, each of these matrices at each step in this row reduction, right, corresponds to a system of equations that is equivalent to my original system. And we just got the sort of specific row which tells me that I'm not going to have a solution. Because remember, this corresponds to the system where I have an equation that's trying to claim 0 equals negative 2, and it cannot, right? So this system has no solution. Now, what that means, of course, is that since this system's solution and this answer are tied together, that B is not in the span of A1 and A2. So because this linear system has no solution, the vector B is not in the span of A1 and A2. All right, so I want to do a couple more things before we wrap this up. We can also sort of think of when we have vectors of smaller length, so we're going to look at an example of vectors of length 3 now. We can sort of tie in some geometric ideas to what's going on here. And I do apologize for my drawing if it's not great. So let's say we wanted A to be the vector, or A1 maybe. Let's say A1 was the vector 1, 4, negative 2. You can think of A right now as a vector in R3. It might look something like this. Of course, the picture is not drawn to perfect scale. So you can think of span of A1 here, where I've just got a single vector. Well, notice this just contains all vectors of the form C1 times A1, right? By definition of the span, it's just all linear combinations of this single vector, which is actually just all scalar multiples of this vector. And so what that looks like geometrically, well, it's just all of the vectors that sort of extend out through this dotted line defined by A1, right? So any vector which lies on this line is in the span of A1. Now let's say we let A2 be the following vector, negative 2, negative 3, 7. Well, A2 might be somewhere here. I'm sort of just guessing. But this might be A2. And what do the span of two vectors in the plane define? Also remember, this is all linear combinations of two vectors. Well, remember we've got this vector A1 plus A2, right? Which is right here. And of course, a1 plus a2 is certainly in the span of these two vectors, right? Because we could just let c1 and c2 be 1 in this equation. And so notice this defines, again, a plane in R2. And so if you think about now just sort of extending this plane sort of infinitely off into space, what the span of two vectors defines is a plane in R2. And so any vector that lies on this plane, so if you imagine taking a vector from the origin and drawing it through this plane, this is what the span of two vectors defines. So you can sort of think of this as like increasing in dimension as we add more vectors, right? That A1 defines a line in R3, span of A1 and A2 defines a plane in R3, assuming some assumptions which we'll talk about later. But for now, just span of A1 and A2 defines a plane in R3. If we take three vectors, well, if we choose the correct three vectors, then actually we'll show later on that the span of three vectors actually defines the entire space R3. So kind of cool. Well, I think it's very cool. And so I want to end with one sort of interesting example of a type of problem that we might start to see more of, and sort of a approach to solving a problem that will be good. So let's let A1 and A2 be defined as above. And we're going to let B be the following vector, 4, 1, H. And so we want to know what values of H cause B to lie in the plane spanned by A1 and A2. And so remember what we just showed, the plane spanned by A1 and A2. Well, this is actually secretly just span of A1 and A2. So if you ask the question, what value, or does the vector B lie in the plane spanned by A1 and A2? This is just secretly asking, is B in the span of A1 and A2? And we know how to calculate that now. But notice, this question is asking something slightly different, right? We don't want to know if this vector B necessarily is in the span, because sometimes it will be, sometimes it won't be. But notice we've defined B to have one variable entry H. So as we've seen, in order to solve this problem, now we want to set up a augmented matrix whose columns are equal to the vectors in question. So notice column 1 is equal to A1, column 2 is equal to A2, and column 3 is equal to B. But how can we row reduce if we don't know what H is? Well, if you remember back to the other example in this video, it turned out that B was not in the plane span, or just the span of these two vectors, when I row reduced and I had that feared row of all zeros and a constant. So what if I tried row reducing, and at the point where I could kind of figure out maybe what H should be, I picked H so that I wouldn't get that issue. And that's how you solve this problem. So what I'm going to do is, again, I'm going to do a couple row operations here. I'm going to pick 1 to be my first pivot column. And so I'm going to do -4 row 1 plus row 2 and replace row 2, and do +2 row 1 plus row 3 and replace row 3. And that gets me the matrix 1, -2, 4, 0, 5, -15, and 0, 3, H plus 8. So I'm sort of taking the approach of row reducing, leaving H alone, and at the time where I can kind of figure out what h should be, then deciding what h should be. So next I'm going to pick this 5 to be my next pivot point, or my next pivot entry. And just to make my life easier, I'll go ahead and divide row 2 by 5. Notice I'll usually do this in row reduction steps when each of the entries in a row is divisible by the same number. So here I just divide through by 5 since everything is divisible by 5. And so now I'm going to do -3 row 2 plus row 3 and replace row 3. All right, so at this point, we are almost done because I've got 0, 0, h plus 17 in the last row. Remember, if h plus 17 is equal to anything but 0, I'm going to get the dreaded 0, 0, 0 constant row that indicates no solution. That would tell me that B would not be in the span of A1 and A2. But I want to find the values of H that cause B to be in the span of A1 and A2. That's only going to be when H plus 17 is equal to 0, meaning this will only be when H is equal to -17. All right, so that wraps up section 1.3. I hope everyone is doing well, staying safe, staying healthy. Again, email me with any questions, and I will see you in section 1.4.